Okay, in this problem we've got the exact same diesel cycle as we did in the previous example. The difference is now we're going to use an air standard analysis instead of a cold air standard. And this is the preferred method where we use the tables as opposed to specific heats. This is the one that's going to give you more exact answers, and I'll show you that as we get through there. So again, what we need to go through here is we need to go and we need to look up our U values. Okay. Oh, well, I guess it depends on what we're looking at. 2 to 3, remember, that's the constant pressure process, the constant pressure heat addition. So I have both work and heat. So again, I have that UPV. So I'm actually looking up H values for states 2 and 3 here. Okay. So, but for state 1, I'm definitely looking up the U value, and then I'm going to use the fact that I know that the compression ratio V1 over V2 is 17. I'm going to use that relative volume over here to go from state 1 to state 2, because this is an isentropic process. Delta S equals 0. Okay, so let's go ahead and look this up. So for 520 degrees Rankine, my U value is 88.62, and my VR, my relative volume, is 158.58. Okay, so again, I get U of 88.62, and I get 158.58 for the relative volume. Now, again, because this is isentropic, I get to use that relative volume, and the fact that I know my compression ratio here, I can find my relative volume at state 2 by taking the relative volume ratio equal to the actual volume ratio, which is 1 over 17 here, right? So then from that, I can calculate VR2 knowing VR1. So it's going to be 1/17 of that, and VR2 then becomes 9.3282. And what I can do with that is I can go and I can look up, again, now I need to look up my H value at state 2, because again, this is a constant pressure heat addition, so I have PdV for the work, and the heat transfer is U plus PV, the change in that. So I'm going to look up my H value, H2. So I use my VR of 9.32, and I'm going to be over here somewhere. I'm going to be just past this guy a little bit, meaning my H is just past this guy, I don't know, like 376 or something along those lines, 378.32. Okay, and that's my H value. And again, I'm using H value because this is a constant pressure. Okay, so I have both work and heat, that U plus PV. This is 378.32. That's set state 2. State 3 is very easy to look up because I've already got the temperature there. So let me just go to 4,000 degrees Rankine, which will be way over here. Okay, and again, I'm looking for my H value here because 2 to 3, again, has both work and heat. So it's U plus PV, which is H, 1088.3. So H3 is 1088.3. And again, I'm using these because my work, I have, it's not constant volume like it was in the Otto cycle. It's constant pressure, so I have PdV. So I have some work. That means Q is that work, PV, and delta U, which U plus PV is H. That's why I use those there. Okay. Oh, the other thing I needed to look up here was VR3 because, again, I'm heading back to state 4, so I'm going to use some volume ratios to figure that out. I'll show you how to do that in just 1 second. But let me go ahead and grab VR3, which is going to be 0.4518. Okay, so now I'm looking for V4. Okay, so I can use the same idea because, again, this is also isentropic. This is an isentropic expansion. Okay, so if I'm looking for VR4 over VR3, that equals V4 over V3. Okay, now the trick to do this, okay, is we multiply and divide by V2. So I get V4 over V2 and times V2 over V3. Okay. What I know here is this is constant volume heat rejection, 4:1. That means I have V1 over V2, which is 17. Okay? And then 2 to 3, that's a constant pressure heat addition. Constant pressure heat addition. Okay? So because of the ideal gas model, right, PV equals RT, if the pressure is constant, R is constant, then V is directly proportional with T. Meaning, instead of using volumes here, what I can do is I can use temperatures, T2 over T3. Again, you know, this guy equals this guy, right? And this guy equals this guy because, you know, the pressure is constant. Right? This is essentially the volume is constant. Okay? So, but here's the thing now. I know VR3, I know my compression ratio, I know my temperatures. I guess I never looked up T2. Maybe I should go look that up quickly so I can get that. So 9.382, you'll remember, was right over here. 9.382 gives me a temperature of, in the range of, be just below that. Yeah, so 1534 and a half. Oops, sorry, 1534 and a half. Okay. So again, I was at 9.3, so in between these two numbers here, so I'm in between these two numbers. 1534 and a half. Okay. So now that I've got all that, I can, of course, calculate VR4. And I get VR4, again, because it's the isentropic process here, I get VR4 equal to 2.9466. I'm going to go look up U value here. Okay, 2.9466. Actually be over here, so it'll be just below that guy. So 420 something. There it is, 421.25. Okay. Find my thermal efficiency. Which is given as that efficiency equals 1 minus U4 minus U1. And this is given in the book over H3 minus H2. And we talked about why we're finding those H values for these and U values for these, right? So plugging in all those values, I get an efficiency of 53.1%, okay? Which is actually significantly different than the 60.3% we found for the cold air standard. So you get almost a 10% difference, or more than a 10% difference, when using the cold air standard from the air standard. This is my preferred method, so if it doesn't state otherwise, this is the way I would do it. I would do it using the tables, using U and H, rather than using the very poor idea that specific heats are constant, which they wouldn't be for these large temperature ranges.